Okay, this is the P4 paper from October 2022. It's question number 10, and this is a modelling with differential equations question in the integration section. We've got all that situation there. When we get down to part C, there's going to be a diagram that we're going to need to use for that part there. So let's look at the rest of it. It says we've got a spherical ball of radius 12 centimetres, which is placed in a bucket of water. What's going to happen is it's going to melt. T minutes is the amount of time taken every time we measure the radius. So T is minutes, R is radius in centimetres. Rate of decrease of the radius of the ball is inversely proportional to the square of the radius. So that's going to be where I'm going to get my differential equations to start off from. And then using the fact we've got radius as 12 and using the fact that we've got those two means that I should be able to get rid of any constants. So let's make a start. As I say, this information tells me that the rate of decrease, let's do it, the rate of decrease of the radius of the ball of ice is inversely proportional to the square. So what does that mean? Well, if it's the rate of decrease of the radius, that's dr by dt, rate of radius. Because it's decrease, in a minute, I'm going to get a minus up here. Okay, now we're going to start off by saying it's inversely proportional. So rather than having an equals, I'm going to have is proportional to, and what's it inversely proportional to? The square of the radius. So inversely means 1 over, and square of the radius means that. So that's my start off position from that bullet point there. We can start off here. If that's true, then I'll change it into an equation by saying if it's proportional to that, then it's equal to minus k over r squared. And now I've got my differential equation, so I'm into solving differential equations. Let's separate the variables. So I'm going to have r squared dr, that's going to go up there. And I'm going to have that dt coming up there. So I'm going to end up with r squared dr is minus k dt. And at that point, we then just integrate. Now, you could put the limits on. I tend not to. I tend to just go through and actually solve it, have some constants, and then work out those constants. But you could put limits in if you prepare to do it that way. So this one, integrating r squared, add 1 onto the power, divide by the new power. With this one, integrating minus k is going to be minus kt. And then I've got to have a constant of integration just on one side of it. So I'm going to end up with that as my first solution. But then they tell me some information, don't they? So they told me that the ball was radius 12 to start off with. So at t equals 0, r equals 12. So if I put that information in, I get 12 cubed over 3 is equal to, that's handy because this bit then disappears here and I just get my constant c there. So c works out to be, in this case, if you tidy it all up, 576. So now my solution becomes r cubed over 3 is minus kt plus 576. And we can now use the second piece of information, which is here, that the radius is 6 when t equals 15. So at, which way around do I want to say? At t equals 15, r equals 6. So if I put that information in, I'm going to get 6 cubed over 3 is equal to minus 15k plus 576, and now you can just rearrange all that. I've already done it previously, so k works out to be equal to 33.6. And what did they say? They said find the equation linking r. So the actual equation that I've got then is going to be r cubed over 3 is equal to minus 33.6t plus 576. It doesn't ask me to write that in any particular way. Underline that one. So I'll just leave it like that there and say get r equals or rearrange to make t equals or anything else like that. Part A, done. where it simply says find an equation linking the two of them. So I've done that. Part B, find the time taken for the ball of ice to melt completely. So if the ball of ice melts completely, R will be equal to 0. The radius will go down to 0. So that's pretty straightforward. Now that I've got my equation here, I can just say when R equals 0 and work out what T is going to be. So R cubed over 3 is 0 equals minus 33.6T plus 576, which means T is equal to, rearrange all that, and we get 17.1 minutes. Going to just keep going back and checking. They haven't said anything about decimal places or significant figures. No, they haven't at all. Okay, so I can go on to the last part. So the last part says, on diagram 1, sketch a graph of R against T. So that's down here. I'm going to sketch a graph of R against T, and we can put on some of the information that we know there. Well, they've already told us on my diagram, but even if they hadn't, I'd be able to work out that that one, we know that at T equals 0, R equals 12, told us that up there. And because of the information we've just worked out here, we know that down here somewhere at T equals 17.1, that's when R is going to be equal to 0. So all we need to know is what happens in order to get from the 12 to the 17.1. Is it a straight line? Is it either the two graphs that I've just drawn in there? And we should be able to work out the information from this by just looking at my dr by dt. So what did we have dr by dt being? Where are we? We've got the dr by dt is up there, isn't it? So what I'm now going to say is, I'll do it sort of here where I can see the graph as well. dr by dt is equal to minus k over r squared, and k was 33.6, I think, so minus 33.6 over r squared. Now, I would always suggest here, just plot some points, okay? We're just going to have we're going to have r going down. So if you plotted 6 and you plotted 3 and you sort of got a sense of what's going on there, I don't actually mean plot them, but I mean work out what they are and see what's going on as we're going through and doing it. But a more algebraic way to do this also would be to say, well, let's just think about what's happening. R is decreasing. So as R decreases here, as R is going to be decreasing because it's going from 12 all the way down to 0 eventually, as R decreases, what happens to minus 33.6 over R squared? We get, if R is going down, R squared will be getting less and less and less. And if R squared is going to be getting less and less and less, then the gradient is going to be getting greater and greater and greater. Just think about that. Okay, so as R decreases, R squared decreases, but because I've got 1 over R squared will be increasing. If this part's getting smaller, then the 1 over R squared will be getting bigger. So what that means is that the gradient is getting bigger as we do that. If the gradient is getting If the gradient is getting bigger, so gradient is increasing, and if that's true, then it's going to be getting steeper. Now, you don't need any of that writing. This is how many marks is this worth? Let's go back and have a look. This is worth 1 mark. So this is all just explaining it to you. The long and the short of it then is it's going to look something like that. So shallower gradient there, getting more and more steep as we progress is the short answer to that part there. But hopefully for that question, that all makes sense.